Hey guys, so we're going to be doing the EE301 12-week review packet, problems 3, 4, 5, and 6, since they're all connected to the same circuit. So let's get started. The first question is to redraw the circuit and express the source in phasor form and the elements as impedances. So the first one we'll do is the voltage source. What we do with these is we just take the peak voltage attached to the equation and we divide it by square root of 2. And then we use that same angle that's right here connected to it. So that's just 30 degrees. So this comes out to roughly 14 at an angle of 30 degrees. And that is in volts, of course. Volts. So the next one we'll do is the resistor right here. So the top resistor, the R10, is just going to be 10 at an angle of 0. Remember, resistors do not have an angle. You don't really even need to put the 0 there, but just in case it helps, we'll do that for now. And that's in ohms. The next one is going to be this capacitor right here. So that's ZC1. And that equation is going to be negative J 1 over omega C. So remember, omega can be found by taking a look at the voltage source. That right there is omega, so that's 377. Negative J 1 over 377 times 221 micro. And that's going to give us like negative J 12. Okay, that can also be 12 at an angle of negative 90. The next one is going to be this 21 ohm resistor right here, the 21 ohm, and we'll say that is just 21 at an angle of 0. Right here, we've got this capacitor again, so another capacitor, same equation as before, negative J 1 over omega C. You may also see the equation written something like this. These will yield the same answer. They're the same, I promise. So that's negative J 377, which is omega, times 530.5, which was negative J 5 ohms, or 5 to the negative 90. Lastly, we have the load inductor, which is going to use the inductor impedance equation, J omega L. That's J at 377, 53.05 milli. And that gives us J 20, or 20 at an angle of 90. And that's how you solve for those. The next problem asks us to find the total impedance. So let's redraw the circuit like the previous one asked us to do. We've got our source here, and now we've got a resistor still at 10. We've got a capacitor now with our neatly labeled negative 12J. Another resistor, which is at 21 still. And then we've got a capacitor here at negative J5 and an inductor, which is at 20J. So the next question is, how do we find the total impedance? So like we normally do, we try to find what's in parallel and what's in series. If you notice, these branches right here all share the same top and bottom nodes. So we can use that to our advantage and say, oh, well, I know that I can add them in parallel. So we're going to find equivalent impedance, and we'll take each branch and we'll add them up. 1 over negative 12J plus 1 over 21 plus 1 over, and then we'll add these two in series to make that branch. So that's negative 5J plus 20J. And that's all 1 over that. So we get, when we add that all together, we get 1 over J plus 1 over 21 plus 1 over 15. $19.82 at an angle of negative 19.3 degrees. And all we have to do to finish it out then is add this resistor right here in series. So total impedance is 10 plus 19.82 angle negative 19.3, and we'll put that in the calculator. And we'll get 29.45 at an angle of negative 12.8 degrees. And that is in ohms. So here is our answer for number 4. So number 5 asks us to solve for all the current values. So we can do that pretty easily by using the current divider rule, which it actually instructs you to do. So the first step is going to be to find the total current. Total current is going to be I source, voltage to the source over total impedance, right? So that's 14 over 30, or sorry, 14 at an angle of 30 over 29.45 at an angle of negative 12.8. And that's going to give us roughly 0.478 at an angle of 42.23 degrees, and that is in amps. Next, what we have to do is we have to just build our current divider rule equation, right? So if you look in your equation sheet on the AC side, you'll see the current divider rule for AC, which is IX equals IEQ times ZEQ over ZX, okay? So EQ is the parallel branch. It's the parallel network. Okay, so IEQ is the current going into the parallel network. ZEQ is the impedance of that network. ZX is the impedance of the branch that we're interested in. And of course, IX is the current of the branch we're interested in. So let's take a look at our circuit again. If, I'll highlight it in green, if this right here is the parallel network we're interested in, that means that the current going into it is IS. So if we're building a current divider rule, IX, then IEQ is going to be equal to IS. Now we need ZEQ. That is actually conveniently, we already labeled it ZEQ on this part of the problem down here. That is the impedance of this parallel network. Doesn't include this 10 because there's nothing to do with the parallel section. So we already have that labeled ZEQ. And lastly, ZX is going to be whichever branch we're looking at any one time. So let's head down here and we'll solve for a couple of these. So I1, that's going to be equal to, like we said, IS over ZEQ, and then the Z of branch 1, the impedance of branch 1. So let's see if we remember that. That was 0.478 at an angle of 42.23. And then our ZEQ was 19.8 at an angle of negative 19.3. And that's over the impedance of our first branch, which was negative J12. And that's going to give us roughly 0.78 at an angle of 130.8 degrees, and that is in amps. Don't be worried if you're like a little bit off. If it's like you got like 0.79 or your angle is maybe a degree or two off, that's almost certainly due to just a rounding issue. The next two are going to be solved the exact same way when we're doing I2. I2 is going to be IS ZEQ, and then that's going to be Z of branch 2, which is 0.478, at an angle of 42.23. And then that's 19.8 over negative 19.3 over the impedance of branch 2, which was just 21. Very motivating answer. And then we'll get 0.446 at an angle of 23.8 or something similar. And then your last one will be I3, which is going to be ZEQ over Z of branch 3. Remember, branch 3 was the one with the capacitor and the inductor in series. So you're going to need to add them up when you do that. So we've got 0.478 at an angle of 42.3. And then we've got 19.8 at an angle of negative 19. And the bottom is going to be negative 5J plus J20. Put that all together and we get 0.625 at an angle of negative 66. And that is in amps as well. And those are the three answers. Remember, the answers we got were this one right here, here, and here. And if I'm not mistaken, this last one, you'll want to take a note of 0.625 at an angle of negative 66, because that is going to be useful for problem 6, which is to find the voltage across the inductor. So that one's pretty easy. If we know which equation to use, we're going to be using Ohm's law. So voltage of the inductor is going to be equal to the impedance of the inductor times its current, which is current 3. So that is, if I'm not mistaken, the inductor was at a value of J20, and its current was at 0.625 at an angle of negative 66, which is going to give you roughly 12.5 at an angle of 24 degrees. Like I said, if there's slight variations in your answer, it's most likely due to rounding. There's a lot of numbers in this problem, so if you use like very exact data, like the number straight from your calculator, you're most likely going to get maybe like half a degree to a degree off, maybe half an amp off. Anything more than that, you should probably check your work over again. So thank you. That was problem 4, 3, 4, 5, and 6 of the EE301 12-week review packet.